Sorry, I just got to adjust that a little short. So yeah, my name's Chris Lapp. I'm a technical solutions architect. So what that means is that I make a bunch of pretty lines and I ask some engineers to solve the problem. So I make a lot of pretty little drawings. So what are we going to talk about today? We're talking about containers. But to get there, we have to have a little bit of background. So I'm sure everybody knows these things, but we are going to cover, what does it mean to be cloud? We're going to cover what a microservice is, going to cover what a container is, then talk a little bit about the video distribution chain, and then come into what the problem is and a possible solution. So what does it mean to be a cloud? It means that you have to have three things. You have to use virtualization technology, you have to have some form of automation, and you have to have a front-end catalog. Now that could be a public cloud, it could be a private cloud, it could be a hybrid cloud, but those three things generally have to be accomplished. Now, to be a cloud-native application, you should always have a microservices architecture. You should always be packaged in containers. You should have a continuous delivery model like a CI/CD pipeline. And you should be cloud managed, aka Kubernetes. So we'll start at what is a microservice. It's a single component of the greater application, to simplify it. It can be individually managed, as each one is independent. It can be modular in nature, and it can be developed and maintained by separate teams across the application. And so what is a container? A container is a type of virtualization technology. I'm sure we've all heard of virtual machines before. It's similar to a virtual machine. It provides a location to host these microservices. It's abstracted at the OS level instead of at the kernel level like a traditional VM. And it's highly accessible and immutable, meaning we can tear them down and bring them back up extraordinarily quickly. So in order to look at the actual problem, we have to have an understanding of what the different traffic types are. So many applications don't fit well into today's cloud-native Kubernetes environments. To illustrate this, we're going to divide the world of applications into a 2x2 matrix. In one dimension, we have whether an application is interactive or whether is interactive or streaming. And we have, in another dimension, the real-time or non-real-time. So Kubernetes is pretty much focused on web applications. And those are squarely in the interactive, non-real-time quadrant. A request is made to a microservice over TCP or HTTP, and a response is returned. There are other applications in the non-real-time world with message buses that you publish a message to without knowing who will receive it, or exactly when that's going to happen. You can deploy a message bus in Kubernetes today, but from Kubernetes perspective, all you see is TCP connections from a publisher and from the subscribers, or possibly a message broker. And you won't be able to route or filter your messages within Kubernetes. So now we actually have to talk about the real-time stuff. Initially, the world out there is trying to solve things like online games, so a lot of people have created their own proprietary systems in Kubernetes to make games work. Why can't we use some of that technology for real-time video? Well, it's proprietary. We all like open standards. So we want to talk about what can we do about live video and maybe why it doesn't work today. Excuse me. So in order to talk about this problem, let's talk about the live video distribution chain. Now, this is obviously an oversimplification. I know we all work in broadcast, and I know this is not what it truly looks like, but as a simplification, the mixer in this drawing is the entire broadcast supply chain, creating the content all the way to where it leaves the building. So how does internet streaming work in this? Well, if I'm internet streaming at the end of that, a client connects to a web server and receives a media playlist. The playlist is simply a list of media segments, and each one typically corresponding to a few seconds of video. For a live event, this server might only return a couple of segments. The client then pulls each segment using HTTP and plays the video in the segment. If it runs out of segments, it simply gets a new playlist, which will have more segments. Typically, each segment is encoded into ranges of bit rates, and the client will try to pull the highest bit rate without causing packet loss. There's been a fair bit of work on low latency live streaming over HTTP, but say to suffice that if you watch football or something on a streaming platform today, there's usually around 30 to 40 seconds of delay. So the process is client gets media from the playlist from the server, client gets media segments, and repeat. Relatively simple. But for video over IP or media over IP, it's a little bit different. There's two models here. The first approach is that the client and server directly negotiate UDP ports, which will be used to send the RTP media. So the client gets the media streams from the URL for the server. The client will negotiate the UDP ports for each stream, and then the server streams the media client to the client over UDP. The second one is how a lot of us see this working using SDP files, where the controller will connect to the sender and get its media description. The controller will then connect to the receiver and sends the media description, and the receiver will join an IP multicast group, an IGMP join. Then the traffic will flow to the receiver from the sender. So, if you wanted to do this in Kubernetes, why does that not work? Why is there a problem? Well, Kubernetes has connectivity options, and so the most popular ones are kubeproxy and node port. That's one of the first ones that existed. These are based on network address translation and port translation. So they work for any TCP application or UDP service, including HTTP. They're orange here because they work okay. Node port can expose services externally. It actually forces you onto a higher port number. So you can't directly negotiate that UDP port through node port, which is why you typically would use an ingress load balancer in Kubernetes. But we're now unable to support real-time media because of this. We're not using the same UDP ports, so we can't negotiate. Next thing you might consider is something a little more popular, maybe a service mesh or a load balancer. If any of you have done any Kubernetes development, one of the most popular ones is IPSHOW. Now, they support TCP apps, and they're really good for HTTP. And so they can route traffic as well, but they typically do not support UDP. They do, however, support QUIC. So QUIC is kind of a UDP protocol, which runs over the network, but it's part of HTTP. QUIC is being enabled in order to enable HTTP 3 streaming specifically for RTP over QUIC. That's about the only support for UDP still in a service mesh. They cannot do real-time media in the sense that they can still not negotiate, and they also don't support multicast. What you'll see everyone out there doing right now when they're running containers is doing everything on one host. Keeping the Kubernetes cluster to a single host means that you don't have to worry about sending all this information between the nodes in the Kubernetes cluster. That's obviously not, why we want to virtualize things. That's kind of just doing a bare metal host with extra steps. So we need to kind of solve this problem. So a friend of mine and me came up with a solution that we called Media Streaming Mesh. And we decided to create an open source project. It's posted on GitHub. We decided that we needed to create something that can do real-time media really well. But we also needed something that could still do, UDP really well. We might want it to do HTTP sometimes, or we could use an IPSHOW service mesh to do the HTTP traffic. We also needed to do TCP for control connections. So we created something that we called Media Streaming Mesh. Now this, again, it's an open source project. We run Media Streaming Mesh control plane as a Kubernetes service with one instance per cluster. And it's worth noting that the control plane can support remote edge nodes without running a local control plane. The Media Streaming Mesh RTP data plane runs as a daemon set on each worker in the node using host networking. And this is the optimal place that we can replicate traffic and also take advantage of high performance networking, or possibly using something like DPDK, which is the development kit that Intel developed. We actually have a prototype data plane right now. It's written in Golang. And we're going to replace that with something written in Rust, so it's a little more robust and has less garbage collection. We also have application pods that automatically inject an MSM stub, as we call it. We call it a stub because it's only 1,000 lines of code, as a small sidecar proxy that redirects application control plane traffic to our control plane. This is done over gRPC and enables us to handle control plane failovers. The stub also intercepts data plane traffic where needed in some cases, so we also wrote that in Rust to ensure that it's high performance and low footprint. So there's also an MSM stub allowing what we call the RTP proxy to handle the control plane traffic in and out of this cluster. We believe that the key to making this project successful will be to make it easy to contribute code without having to have deep knowledge of the entire code base. To that end, we're making the control plane pluggable as well. So for example, you can replace our current RTSP beta control plane with anything else. We actually used librtc as our data plane and control plane. And so you can take any library existing out there because it's written in Golang and just pop it in. And so I wish that NAB was 1 week later, because my counterpart Giles is actually at KubeCon in the UK right now giving the keynote speech. And I promised him that I'd save our live demo of this actually working for him for that keynote. Otherwise, I'd have a live demo for you. But this is what the demo setup looks like, and we're actually using it to stream HLS video through the data plane. Now, Why did we think that we needed to do this? Well, first of all, the problem needs to be solved. We already have multiple vendors out there adopting our control plane and our data plane. You might hear from some of them today if you stop by our booth. But why else did we do this? Well, we also need something that has all the benefits of a regular service mesh. First of all, it needs to be observable. You need to be able to monitor it. It needs to have high security, reduce the threat vectors for the Kubernetes cluster. We need to have reliable distribution so we can replicate streams optimally, and we need to be very deployable. There's also an option later on where we could do something like Spiffy Spire or use the open policy agent to do security authorization as well. Because our control plane is modular, we can pop pretty much anything in there. So I have one call to action. If you want to see Media Streaming Mesh, if you want to contribute to Media Streaming Mesh, if you want to download Media Streaming Mesh, or you want to just hop on a call and talk about it, we do hold bi-weekly calls for the open source project. You can contact me, Chris at Cisco, or my counterpart, Giles. We operate in 2 different time zones. He's in UK, I'm in Eastern, so message whichever one's closer to you. And with that, I'll take any questions.